Alrighty. Good morning, everybody, and welcome back to Real Analysis. So, plan for today, we're going to continue our discussion of cardinality. Office hours this afternoon, canceled. Office hours tomorrow, TBA. Basically, based on like how the roads and stuff are tomorrow, I'm hoping to come in tomorrow and do in-person office hours, but if I don't, I will do virtual office hours from home. And I'll send out an email tonight or tomorrow morning about that, and if I end up doing it virtually, I'll send out a Zoom link, etc. Homework. Homework 2 is now due Friday. Homework 3 will be posted right after class and will be due next Wednesday. Also, homework 3 is also focusing on some properties of cardinality. So, to my 11 a.m. students, I'm sorry, apparently you didn't get the email when I sent it out this morning. I hate how Canvas doesn't let you send emails to multiple classes at the same time. But that's my problem. Any questions or comments before we get started for today? All right, for our joke of the day.
Oh, that's so funny.
Hey, where did you want?
Oh, and you broke it, Josh. Good going.
Oh, yeah. Hold on. Yeah, there we go.
You know, it's really nice to project.
Oh, yeah.
I come in here pretty good.
Tonight's forecast. A freeze is coming.
Allow me to break the ice.
You're not sending me to the cooler. Freeze well. What killed the dinosaurs? The Ice Age! Stay cool, bird boy. Let's kick some ice.
Show some mercy.
I'm afraid that the conditioners left me cold to your pleas of mercy. All right, everyone. Chill. It's a cold town. Cool party. Can you be cold, Batman? Yeah. To perfection. Revenge is a dish best served cold. Winter has come at last. Freeze. Freeze! Ice! Freeze! Icy winter forever! Frozen! Icy! Freeze! Winter ice! Freeze! Winter! Winter! Freeze! Cold! Frosty!
Okay. Today's joke of the day brought to you by Arnold Schwarzenegger. He went on to become governor of California.
Is that the joke?
Yeah. Well, no, the joke is just all the whole difference.
Cool.
Okay, so, oh gosh, where do I have to pick up? How do I pick up from here? So when we last left off class, we had talked about a few different things. We had said that a set S is countable if one of two things happen. First, either it has the same cardinality as the natural numbers, and in that case, we say that S is countably infinite. Or, if our set S is finite, and as you recall, I went on this big rant on Monday about if it's finite, then the book doesn't call it countable, but every mathematician I know would call it countable, so we're going to call it countable. We also showed two things last time. We showed, first of all, that Q is countable. In other words, that the natural numbers have the same cardinality as the rational numbers. And we also saw that the real numbers are not countable. And our proof of that was sort of this argument involving This is proof involving looking at the diagonal and saying if we did have a one-to-one correspondence from the natural numbers to the reals, then we should be able to list out all the real numbers, but we couldn't even get all the real numbers between 0 and 1. We couldn't even get all the real numbers whose decimals only consisted of zeros and ones into a list. Therefore, there was not a one-to-one correspondence possible from the natural numbers to the reals. And that's where we left things off. So, a little bit of history about this one. This proof that we looked at, that the set R is uncountable, is called Panthers Diagonalization argument. Which is called the diagonalization argument because it consists of, suppose you have a list of every real number whose decimals are zeros and ones, look at the diagonal, make a new number that's not in that list by making it be different along each diagonal entry. As proved by George Cantor, who is a German mathematician, worked in the late 1800s. And he's basically known as the father of set theory. Basically, this is the guy who kind of invented a lot of notions of like what it means to compare sets. Anything that you've seen in a previous math course involving set theory, George Cantor probably had his fingers in it. And before you ask, yes, his name does not have an E at the end. Spelled George, G-E-O-R-G. Any questions or comments about the diagonalization argument before we move on? So I have a question. We now know that the natural numbers as an infinite set are smaller than the set of all real numbers. Does there exist anything in between? In other words, does there exist a set S with the size of S being strictly greater than the size of the set of all natural numbers, but whose size is strictly less than the size of the set of all real numbers? What do y'all think? Can we find some set that is strictly bigger than the natural numbers, but strictly smaller than the real numbers?
I don't really have like a really like polished idea, but is there a way to take like some infinite subset of the real numbers that would still be bigger than the naturals? And
Give me a subset of the reals.
no, I don't know. This is why I didn't want to say this. Could you, I don't know, like find some like real numbers that follow some like specific pattern that would go off to infinity? Like kind of like the rationals or like the quotients of integers. Could you find something similar where you take like some increasing sequence of like almost like what we did with the digits of pi or something like that, where you keep like writing it as a sequence of rationals, but then obviously I don't think that would work, but something kind of like that. I don't know.
Let's say any subset of the rationals is either going to be finite or have the same cardinality as the rationals, which, by the way, as we've seen, is the same size as natural numbers. So I don't think we could get there by taking any subsequence of the rationals, for instance, or something of the same size as a subsequence of rationals. Okay?
Are the irrational numbers the same size as the real numbers?
Good question. How about the irrational numbers? Fortunately, they have the same size as the real numbers.
This is purely intuitive, and I have absolutely no proof. But it seems that there's a binary between things being uncountable and countably infinite, so then there's a binary in their size.
So you think everything has to be either countably infinite or uncountably infinite? It is true that, well, when we say uncountable, by the way, that just means not countable, which means bigger than the natural numbers. It's not necessarily going to turn out to be a binary thing. We're going to see in our next packet that there's, spoiler alert, infinitely many sizes of infinity. So it's not going to be a binary thing, necessarily. It's good intuition to think about, though. And that everything, kind of all the sets we've seen so far, all the infinite sets we've seen so far do kind of tend to fall into one of two categories. Either ideas? So, turns out this is a bit of a trick question, because the answer is, it's unknown. This is actually one of the biggest sort of unsolved problems in math for a long time. There's a hypothesis in math called the Continuum Hypothesis, which basically just says the answer to this question is no. So no such S exists. Meaning that that it's impossible to have a set that's bigger than the naturals but smaller than the reals. So this was actually first proposed by Cantor in 1878. And Cantor tried to ask this question of, he figured out that the reals are strictly bigger than the natural numbers, but asked the question of, is there something in between? He thought that the answer was no, there's nothing in between, but he wasn't sure about it. He couldn't find a way to prove it. So he first proposed that, I think that the answer is no in 1878, and then mathematicians for a very long time tried to work on this problem. Has anyone ever heard of David Hilbert? His name kind of tends to pop up. Those of you taking non-Euclidean geometry, you're probably sick to death of the name Hilbert. David Hilbert was a mathematician in the late 1800s, early 1900s. He's often kind of referred to as the last mathematician who's kind of did math, who basically did good work in every branch of math. You look at a modern mathematician and you might see them do work in a couple areas in math, but you're not going to have them doing work in kind of every branch of math. David Hilbert kind of had his fingers in every mathematical pie to different extents, especially in pure math. And there's a reason why the two professors in this department who debatably know the most math are David Gabler and David Murphy. And Davids. You know. Anyways, at the dawn of 1900, David Hilbert proposed a list of the 23 greatest unsolved problems in math. In 1900. Basically, he said, like, hey, at this big mathematics convention, here are the 23 biggest problems among all of math that are still unsolved to this day. These are the problems that are going to define mathematics going forward in the 20th century. Proving the continuum hypothesis, or disproving it for that matter, was number 1 on his list. In other words, proving or disproving that there was no set whose cardinality is strictly between the natural numbers and the real numbers, according to David Hilbert, was the greatest unsolved problem in mathematics of the time. So when I ask you all this, if you would If you had given me a definitive answer, I would have been super impressed, by the way. Yes?
Just out of curiosity, how many of those 23 have been solved?
Define solved.
Not unsolved.
So, most of the 23 since then have had progress made on them. Some of the problems are not definitively like yes or no questions, and they're just like questions like exploring the properties of finite simple groups or something. So not all of them are definitive things that you could equivocally say have been solved or not. But pretty much all of them have been worked on since the time of Hilbert. A lot of, I don't know, I forget offhand. If you Wikipedia, it has a list of all 23 of them and the progress that's been made on each one. Some of them still remain unsolved to this day, like Riemann hypothesis, for instance. But yeah, these kind of 23 problems Hilbert came up with, kind of motivated mathematical thought for a long time. But the continuum hypothesis was given an answer of sorts by Paul Cohen in 1963. What did Cohen prove? Cohen proved that this question of does there exist a set whose cardinality is between the natural numbers and the real numbers is logically independent of the ZFC set theory axioms. So what does that mean? So, if you remember, a couple weeks ago we kind of went through all of our axioms of the real numbers that we were going to use throughout the semester. The field axioms, the order axioms, the axiom of completeness. There's a bunch of axioms for how sets behave in general that we didn't talk about. We're kind of going to inherently assume. And those are called the ZFC axioms, the Zermelo-Franken axioms of set theory, with the C standing for plus the axiom of choice. Basically, these are the axioms that modern mathematicians kind of inherently assume, whether they know them or not, by heart, and are kind of the foundational set theory axioms. Although, if you take Dr. Gabler's logic class, he may have something else to say on the matter. What Paul Cohen proved is that the continuum hypothesis is logically independent of these axioms. Meaning, it is impossible to prove that there exists a set S whose cardinality is between the reals and the natural numbers. It is also impossible to disprove. And when I say impossible, I don't mean very difficult. I mean literally impossible. From the set theory axioms that are commonly used, axioms that mathematicians were working with, to show that there either does exist or does not exist a set S whose cardinality is strictly in between the natural numbers and their reals. So what does this mean for the continuum hypothesis? What it really means is that the question of does there exist a set with cardinality in between, it depends on how you define everything. You can define the real numbers in a way such that you can find an answer. You can also define the real numbers in a logically consistent way that the answer to this question is no. In other words, I can't really say that there is a good, strong answer, yes, yay, or nay to this question. In fact, it is logically impossible to do so. Kurt Gödel, the guy behind Gödel's incompleteness theorems, tried for a very, very long time to work on the continuum hypothesis. And in fact, a lot of his work on the continuum hypothesis kind of led into his incompleteness theorems about inconsistency versus completeness of mathematical logic. Yeah, if any of you are taking Dr. Gabler's logic class, you should ask him about the continuum hypothesis, and he'll try to tell you a thing or two about how it ties into a lot of the key concepts in that class. Question number 1 on homework 3, does there exist a set S? No. I'm good. Any questions or comments about the continuum hypothesis? This is not something I'm going to ask you to like prove or like necessarily even read necessarily about, but it's kind of a cool piece of mathematical history that I figure if we're talking about cardinality of infinite sets, I can't not mention the continuum hypothesis. It plays such a big role in that. Alright, and with that, it's time to move on to cardinality 2. So first thing I want to do, so the last packet was kind of focused on looking at specific sets of numbers that we've seen, the natural numbers, the reals, the integers, the rationals. We're kind of looking at them. On this packet, I'm going to prove some more general theorems and look at some more generalized results relating to the ideas of countability and cardinality. Specifically, I want to show two things in this packet. First of all, that sharing two-set sharing cardinality forms an equivalence relation, which we'll define what that means. And second of all, proving that there are infinitely many sizes of infinity. So me and Laurie are looking at each other because they had all sorts of fun in discrete last semester looking at equivalence relations. So first of all, we didn't actually in the last packet.
I don't have the right packet. This is.
No, you know what? You don't want to learn about information sets?
I really do not.
Does everybody else have the right packet? It should say cardinality 2 at the
I
top.
think this might be your notes.
That ain't my notes. That's a packet for game theory today.
You're very good.
My apologies. So first of all, we need a way to be able to say that one set is strictly smaller or bigger than another one. Because technically, we didn't do that in the last packet. We talked about what it means for two sets to have the same size, but it'd be nice to have a way to kind of compare the size of two infinite sets, basically saying which one is smaller or greater if they're not the same size. And we're going to say that given two sets A and B, that the cardinality of A is less than or equal to the cardinality of B if there exists a one-to-one function f from A to B. So what does that mean? So basically, A has a size to it that is smaller or equal to B size if we can find a one-to-one function, not necessarily onto, from the set A to the set B. So let's do a little graphical example here. John, give me a number 2 through 5.
3.
3. All right. Jack, give me a number 4 through 6.
5.
All right. So let's say we want to look at a set A with 3 elements and a set B with 5 elements in it. And I want to prove that the set A is smaller than the set B. And for whatever reason, I'm not going to just say 3 is smaller than 5. So what it means for cardinality of A to be less than or equal to cardinality of B basically means I can form a one-to-one function. Somebody remind me, what is a one-to-one function? Yeah, Peter?
A function where if the outputs are the same, the inputs have to be the same.
Yeah, in other words, no two inputs map to the same output. Every input gets mapped to something unique. So one way you could think about being a function, having a one-to-one function from A to B is that there are at least as many elements in B as in A, so that everything in A can get mapped to something unique in B. Because if A had like 6 elements in it, for instance, instead of 3, there wouldn't be a way to form a one-to-one function from A to B. We could say this element maybe maps here, this element maybe maps here, and where would our 6th element map to? It's got no choice. It has to map to something in B that's already been mapped to. And as soon as we do that, our function is no longer one-to-one. Because we have 2 different elements, D and F, here in the set A, that map to the same output in B. So in order for our function to have a one-to-one function from A to B, B has to have the same number or more elements as A does. Any questions or comments? So let's flip this around. How do you think we could say that the cardinality of A is greater than or equal to the cardinality of B? Well, Dr. Gerstle, cardinality of A is greater than or equal to cardinality of B if there exists a one-to-one function S from B to A. Okay, that's not wrong. But is there a way we could do this other than just kind of taking this definition here and just literally flipping the order of the 2 sets around? Okay?
If the function A to B is onto, that means there exists an input for every element in B.
Yeah, exactly. We're going to say that the cardinality of A is greater than or equal to the cardinality of B if there exists an onto function. From A to B. With the idea being, let's say now we have 5 elements in A and only 3 elements in B. If we can find an onto function from A to B, that means every element in B is going to have something from A mapping to it. And then potentially more than one element. If we did something like, say, this. So if we have an onto function from A to B, that means that every element in B gets mapped to by at least one element in A. And if everything in B gets mapped to by at least one element in A. Question here?
Yeah, I was just wondering, would there ever be a situation in which it makes, instead of looking for a function that is, like to establish equality of cardinality, instead of looking for a function that is both one-to-one and onto, you could look for like different functions, one of which is one-to-one and one of which is onto?
Good question.
Would that be easier in some cases?
Prove that the 2 sets have the same cardinality by showing less than or equal to and greater than or equal to separately? It's a good question. Turns out it would be logically equivalent to do that.
Okay.
That if you can find a function from, say, A to B that is one-to-one and a function from A to B that is onto, not necessarily the same function, you can do those 2 things if and only if you can find a single function that satisfies both conditions.
Yeah, I was just wondering if it was like easier to do that in some cases, or whether mathematicians ever do that, or is it almost always easier to just find the one function?
definitely be easier to find two separate functions. You don't have to worry about both properties at the same time. Can't think of an example off the top of my head of something where it would specifically be easier to do it both ways or to do two separate than one at the same time. But if you're having trouble finding one-to-one and onto at the same time, but can do them separately, turns out that that's the same.
Okay.
That's the Cantor-Bernstein theorem, which is in our textbook, but we're not going to do it in class because it's lengthy and tedious, and I just don't want to. So, if we say that if there's an onto function f from a to b, then every element in b gets mapped to by at least one element in a. So a has to have at least as many elements as b. Because since everything in A can only map to a single element in B, in order to have an onto function where everything in B gets mapped to, A cannot have fewer elements than B does. And so what this gives us is a way to kind of compare the cardinalities of two sets that could be finite or infinite. Obviously, if you have a set with 3 elements versus a set with 5 elements, the 5-element set is bigger. But this gives us a way to say, for instance, we can't show that, or we know that the real numbers and the natural numbers do not have the same size. This is going to give us a way to determine which one is bigger than the other. So if we go to the second page, we can actually now fully prove that. So if we wanted to prove now that the natural numbers cardinality is strictly less than the real numbers cardinality, we need two things. First of all, we need that they're not equal, that the cardinalities are not the exact same. And second of all, we need that the natural numbers have cardinality less than or equal to the cardinality of the reals. So I'm going to say, first of all, we know that the cardinalities are not equal by Panthers Diagonalization argument. Second, we know that the natural numbers are going to have cardinality less than or equal to the reals because there exists some function f going from the natural numbers to the reals that is 1-to-1. Can anybody give me a function that takes in natural numbers and spits out real numbers that is 1-to-1? Meaning no real number is going to get mapped to multiple times. Okay.
F of x equals x.
F of x equals x. You take in a natural number and you spit back out the same thing as a real number?
Yes.
Well, let's see. If we have two elements, if f of a equals f of b, does that necessarily mean a equals b? I would say so. By definition, it says 1-to-1. If f of x equals a equals f of b, then by definition, a has to be equal to b. So that this will give us a 1-to-1 function from the natural numbers to the reals. Therefore, cardinality of the natural numbers is no bigger than the cardinality of the reals. And since we know that they're not the same cardinality, that's going to tell us that the cardinality of the natural numbers is strictly smaller. Any questions or comments about that? Oh, let's flip this around. Alternatively, instead of finding a 1-to-1 function from the natural numbers to the reals, we could find a function from the reals to the natural numbers that is onto. There exists some Can anybody give me a function that takes in real numbers and spits out natural numbers in a way that is onto? Meaning every natural number is going to get mapped to by at least one real number.
The floor function?
Gadzooks! Spoiler alert for homework 2. But the floor function is one function that'll do the job. The floor function is a function that takes out in reals, spits out natural numbers, and every natural number does get mapped to by at least one real. By infinitely many reals, in fact. And so, either one of these two things, there being a one-to-one function from the natural numbers to the reals, or an onto function from the reals to the natural numbers, the existence of either of those is enough to tell us that the natural numbers have to have cardinality less than or equal to the reals. And then Panthers Diagonalization argument tells us that they're not equal to each other. So the natural numbers are strictly smaller. Any questions or comments? We know we can't find a onto function from n to r, we can't find a one-to-one function from n to r, or an onto function from n to r, because if we could, that would prove that the two sets have the same cardinality, which Panthers Diagonalization argument says is impossible. But you can find one-to-one from n to r, as well as onto from r to n, and either of those alone would tell us that the cardinality of n is less than or equal to cardinality of r. Questions, comments, concerns? So before I move on to kind of our first major proof of looking at cardinality, in this packet at least, the proof that cardinality defines an equivalence relation on sets. We need to talk a little bit about inverse functions. Which is to say, if and I'm on page 3 now in the packet, from A to B happens to be a one-to-one correspondence, we can define the inverse function f inverse as a function from the set B to the set A is going to be defined in a way where we take some element, little b, and it's going to spit out the element in A, satisfying that little f of A is equal to b. So in other words, if little f of A is equal to b, then our function f inverse, little f inverse of b, is going to be equal to that element A. And this is something we need one-to-one correspondence in order to define. So if we do a quick example, let's say we want a function f going from, r to r, and it's going to be defined by f of x equals x cubed minus 3. If I plug in 1 into this function, I'll get 1 cubed minus 3 is -2. So if f of 1 is equal to -2, what does this tell us about our inverse function? That f inverse of blank should be equal to blank, according to our definition up here.
F inverse of -2 should be equal to 1.
Yeah, exactly. Since f F inverse just does the same thing as F, but backwards. F inverse of B equals A if F of A equals B. The fact that F of 1 is negative 2 should tell us that whatever our inverse function is, F inverse of negative 2 should be 1. And the fact that F of, say, 0 gives us negative 3 should similarly tell us that F inverse of negative 3 should give us 0. However, our inverse function is defined. How would we go about finding a formula for F inverse? Be nice if we could just say something like F inverse of x equals expression in terms of x.
Would you switch x and y and then solve for y?
Exactly. Yeah, so to find a formula for F inverse, what you're going to do is treat this as y as a function of x, swap your x and y, and then solve for y again. So we're going to swap x and y, then solve for y. So if we do that, we'll get that x is equal to y cubed minus 3. And if we solve for y, we'll get that y cubed is equal to x plus 3. That y should then be cube root of x plus 3. And that's going to tell us our formula for the inverse function, f inverse of x is cube root of x plus 3. Which if we check, we can see that if we plugged negative 2 into this function, we get negative 2 plus 3 is 1, cube root of 1 is 1, and so we would indeed get that f inverse of negative 2 comes out to positive 1. And similarly, if we plugged in negative 3 for x here, we get cube root of negative 3 plus 3. That's just cube root of 0, which is 0. Therefore, f inverse of negative 3 does give us 0, in fact. So this gives us a way of kind of solving for our inverse function. Question. Why does our function have, why did I specify that to have an inverse function, f needs to be a one-to-one correspondence? What I would like for you all to do, instead of answering right now, go ahead and take a minute and talk with your neighbors about why do you think I specified in this definition that f had to be a one-to-one correspondence? And in particular, if f is either not one-to-one or not onto, what goes wrong in our definition? Go ahead and take a minute or two, talk with your neighbors, and see if you can figure out why I made that specification here.
Because if you have some element of the range, that is not the element, or is not the image under the domain, if you plug that into the function, the inverse function, it won't map.
No, wait, it's not. I think I'll be wrong. I know it's
What the one without because we discovered this two cardinalities. I feel like that's the guy.
If it's on having that one. For some reason, I thought I was talking about by section, yeah, which is, yeah.
Inverse function and so that. So if the function is 1 to 1, then the inverse function inverse
That was a classic. Remember the one time when you brought in the two guys? Said Gabler.
I thought you said 1-to-1.
Oh wait, no, because so
No, I
if
didn't.
you have 1-to-1,
But for like 5
then
minutes.
some.
1-to-1 corresponds between 1 and over 2 by Joe. That's how I say it. I think the term 1-to-1 corresponds to
The guys,
and
the
2
guys
long.
so like, watching you guys like it's gotta be
Subjective and objective, which one is which?
I don't know. I never kept
It's not the same, then it means that it's the inverse.
So it is free time. Is free time
It's
smoking, arson, fast car, fast Oh yeah.
the inverse, okay.
It's like
It would, yeah.
And if it's not then not every input will have an output. Yeah. Okay.
Are you free after that?
I think we would, yes.
No.
I don't know.
Usually younger children.
I don't know why I keep
You wanna talk about-
frustrated.
That's gonna sound like.
I have to talk to like today for Marquette. I'm just curious if you know anything about Marquette.
Ooh, okay. I don't know much about Marquette's grad program.
Maybe it's like their computational sciences as their PhD and they're interested in my application, so that's exciting.
That is good news.
Yeah, so they just didn't know that they had to made it sound like it'd be
So it's interesting, yeah, because usually you don't get interviewed for,
Yeah, no.
for the
U
program.
of M is doing interviews this year.
Yeah.
And U of M for their both their PhD programs.
Good for them.
They only had, it was weird, they had like 800 applicants for their math PhD program, but for their applied one, they only had 200 applicants.
Is he a program like how many like current students they have? Is it comparable for each, do you know?
I didn't look at the pure math program in terms of size. The current applied program's probably like 30 or 40 kids.
Okay.
So
I would say, I imagine their pure program's probably a little bit, it's probably bigger, but I don't know if it's that degree bigger.
yeah, I didn't look at it.
Alrighty, let's come back together.
Yeah.
So, what goes wrong if f is not a 1-to-1 function, if we try and define an inverse function?
Well, f inverse is supposed to be a function, so if f is not 1-to-1, then the inverse would have to split and cover two different values in the original set.
Yeah. So what would go wrong is we would have something like f of a1 equals f of a2 equals b for some a1 not equal to a2 elements in a. So little f of a1 equals little f of a2, and that's b. What would f inverse of b be? dB. Well, by definition, since f of a1 is b, f inverse of b would have to be a1. But since f of a2 is equal to b, f inverse of b would also have to be equal to a2. And that can't happen if we want f inverse to be a function. We can't have f inverse take a single element in b to multiple elements in A without breaking the fact that it's a function. Which can't be. Yeah, so if our original function's not 1-to-1, then our inverse function would map we have to map one thing to multiple things, and a function shouldn't do that. What goes wrong if our function f is not onto?
Our codomain becomes the domain of the inverse function, and so we'll have elements in the domain of the inverse function that we cannot plug into the inverse and get outputs.
Yeah, there's something in our codomain that doesn't get mapped, or there's something in B that won't map to anything in A under that mapping. Is that essentially what you're going to say? I would agree. I would say then some element little b and big B has no element A and A mapping to it under F, which then tells us in turn that F inverse of B cannot be any element and A, which again breaks their definition of a function. You can't have F inverse be a function from B to A if there's some element in B that doesn't get mapped to anything. That's bad. Any questions or comments? Okay. So we have to have a one-to-one correspondence in order for our function from A to B to be invertible, to have an inverse function. Because if it's not one-to-one, then you can have something in B mapping to multiple elements in A. If it's not onto, then you'll have something in B mapping to nothing at all in A. And either of those would kind of break our definition of what it means to be a function from B to A. All right, it's going to do it for today. You'll have a good rest of your day. I will see you all on Friday. Okay, so homework 2 will be due Friday. Homework 3 will be up on Canvas very shortly.